Good morning. I'm Dale Hoffman, and along with my colleague Tim Crowder, would like to thank all of you for attending this webinar. We'd also like to thank Megan, Corey, and CEE for hosting it. Tim and I are here to share our thoughts and data on innovative testing techniques for HVAC. In many places, energy efficiency programs have been around for so long that we're seeing high-efficiency equipment being replaced. Some utilities and states have already increased their equipment baselines. For example, the furnace baseline in Iowa is 90%. Also, equipment standards continue to rise, and it's forecasted that they will rise even further. Programs are facing stiffer energy efficiency goals and unlimited budgets. So one solution is to dig deeper into heavier marketing and outreach to get your programs in front of consumers and businesses that have not previously been on the radar. Unfortunately, these strategies can be intensive and expensive. And we're also hearing more and more about behavioral programs and new technologies such as digital controls and energy management systems, and innovative program designs such as moving upstream. While some of these emerging program designs show promise, the risk of failure is high and the return on ratepayer dollars is difficult to measure. And finally, we're also seeing performance-based programs that compare the real before and after impact of specific energy efficiency measures. Measured impact does not allow for conservative estimates or for an evaluator to discount your impact. Performance programs also account for both improvements in hardware and improved installation and maintenance processes. Two of the more popular performance programs are commissioning and retro-commissioning of larger buildings and home performance, such as Home Performance with Energy Star and Energy Star New Homes. Today, we're going to talk about another performance program, HVAC performance.
Hello everyone, this is Tim from Elevate Energy. Elevate Energy is a nonprofit organization with a triple bottom line mission: economics, save money for households, building owners, and communities; environmental, using energy efficiency techniques and conservation to protect the environment; equality, to make sure the benefits of energy efficiency programs are available to everyone, especially those in communities who are often underserved. To do this, we promote smarter energy use for all. We give people the resources they need to make informed energy choices. We design and implement energy efficiency programs. We ensure that the benefits of energy efficiency reaches those who need it the most. Here's a picture of our team, who is comprised of a diverse array of professionals with experiences ranging from technical focus on construction, energy efficiency, to policy on housing and utility regulation. I hope you'll visit our website and learn more about us.
Midwest Energy Efficiency Alliance and Energy Stewards International have offered HVAC System-Adjusted Verified Efficiency, or SAVE, training for over 4 years now. Last year, 13 members of Elevate Energy staff and 12 of our contractors participated to enhance our understanding of furnace efficiency and to develop the workforce we needed to fulfill the task at hand, which is measuring and verifying efficiency rather than assuming the AFUE is indicative of system performance. We're wasting billions of BTUs because our workforce is either undertrained and others are just inclined to install the code minimums. To address this challenge, MIA, in partnership with ESI, developed a program that allows HVAC contractors to easily diagnose and improve the performance of a furnace. This training program and contractor certification is named HVAC SAVE, System Adjusted and Verified Efficiency. I first met Tim Haynes of ESI about 10 years ago when I took an HVAC class in Iowa, and I've worked with him several times since. Much of this class is common sense when you really think about it, but it's also supported with a lot of data. I think Tim would agree when I say prescription without diagnosis is malpractice.
So for today, we're going to first take a look at furnace system efficiency testing, this HVAC performance. Then we're going to look at some of the tests that make up system efficiency. We're going to take a closer look at one of those tests, and that's static pressure. After that, we're going to switch gears and look at benefits to the different stakeholders groups. Then we're going to look at how us as Elevate have decided to implement SAVE into our programs, our large multifamily program. Then we're going to also look at the trends of SAVE program.
So what is HVAC performance? Unfortunately, the industry hasn't settled on standard language. Sometimes it's called commissioning, system efficiency, right sizing, or performance tune-up. By any definition, HVAC performance recognizes that real efficiency does not equate to rated efficiency. In fact, that real efficiency is something less than rated efficiency. I've seen many furnaces that were rated 95% AFUE that were operating at less than 70% system efficiency. HVAC performance also recognizes that the contractor has an impact on real efficiency. Unfortunately, a furnace, heat pump, or air conditioner is not simply plugged into the wall and you're done. There's a lengthy installation process guided by a 60 to 70-page manual and performed by a seasoned, certified, and sometimes licensed professional. To assume all those professionals perform at the same level of work and that it's always perfect is not borne out in our field data. Rather, HVAC performance considers the impact the contractor has on the installation, commissioning, recommissioning, and sizing and selection. These processes are particularly impactful in a more difficult replacement environment. So HVAC performance shifts the evaluation of efficiency from out of the box, as determined by a handful of engineers in a lab environment with nothing attached to the furnace, to installed and operating, as that specific box is performing within a specific system. In fact, the fundamental principle of HVAC performance and the HVAC SAVE program is that operating efficiency is a far better measure of true efficiency since it is measured and not deemed. Furnace AFUE is determined by engineers in a lab, while HVAC performance measures everything added to the furnace in the field. It's easy to assume if you have a brand new furnace or air conditioner in your home that the equipment is operating at peak performance. Unlike other appliances in your home, such as a refrigerator or stove, your HVAC equipment cannot just be taken out of the box and plugged in. Your HVAC equipment depends on a series of ducts and registers winding through your unique home, and if the new unit is not properly matched with the existing ductwork, your equipment may not be operating at its optimal capacity. If the equipment isn't operating as efficiently as possible, it means higher monthly utility bills, decreased comfort, decreased indoor air quality, and possibly higher maintenance costs. This graphic depicts the components of HVAC performance. If any of these measures or calculations are outside of manufacturer's specifications, optimal efficiency will be affected. HVAC performance testing has 5 components. Static pressure is the resistance to the airflow in the system. Temperature rise is the rise in temperature in the heating mode. Manufacturers typically provide a range, which is usually around 40 to 70 degrees. The drop refers to the decrease in temperature when the air conditioner is running, and that's typically around 20 degrees. BTU loss is the measured loss of heat between the furnace and the registers, while CFM loss is the comparative measurement between the output at the furnace and what comes out of the registers. Last, combustion analysis measures flue gases for oxygen and carbon monoxide to determine the percentage of unburnt gas. In addition to testing, calculating heat loss with modeling programs like RightSoft and the use of AHRI certified components, which addresses matching furnaces with coils, will ensure the equipment chosen is the correct size.
This chart shows the results of 507 system tests conducted by contractors back in April of this year in Western Illinois as well as in Iowa under the SAVE program. Each one of these vertical lines you see represents individual units that were tested by a SAVE qualified contractor. In those existing homes that were tested, the equipment had an average save score of 72. As you can see from the chart, a passing score is 85. A save score is like a conversion efficiency ratio that basically compares energy out to energy in. Using measurements taken in the field to assess current operating efficiency, this month only 16% of systems that were tested passed to the save standard. This is a significant sampling size, which is backed by a DOE study titled Energy Savings from System Efficiency Improvement in Iowa's HVAC SAVE program, where in this study the results were very similar. Here's an example of a typical 80% efficient 4-star furnace. There are 4 measurements that need to be taken to determine the system static pressure. The first is before the filter. Please note that with all test locations, you will need to be sure that the static pressure tip is always pointing in the direction of airflow. The second test location is at the blower cabinet. When testing here, you want to be sure that none of the blower components come into contact with the pressure probe. The third testing location is at the heat exchanger cabinet. There are a few safe options when testing here: removing the high limit switch and using this as an access hole for a test location. This should be tested in a safe area not to damage the heat exchanger or any other components. Another safe test location is 2 inches down and 6 inches from the rear. Always be sure to check the manufacturer's drawings before you drill any holes. The fourth and final test location is after the A coil. Again, as with all test locations, care must be taken not to damage components. This video is only showing one of the total system efficiency tests. To ensure a system is operating at peak performance, other tests are required. So what do you do after you take those measurements? After you take the measurements, you'll be able to determine the pressure drop over the filter. You'll be able to determine total external static pressure as well as the pressure drop over the A coil. If the pressure drop over the filter is too high, this is a sign that the filter is too restrictive. The causes of this restriction could be a dirty filter, wrong filter type. Also, a pressure drop over the filter could also mean it's an issue with the return. If the pressure drop over the A coil is high, this could be a sign that the A coil is dirty or it's not sized properly for the equipment. If you have too much total external static pressure, this could be a sign of a few different problems. Other tests will be needed to confirm the issue. These results could tell you if you needed to address the fan speed setting or if you needed to add some more supply or return ducts. Some of these tests are relatively inexpensive, such as replacing the filter, tuning the combustion, or balancing the system, while other tests are more costly, like adding returns, supplies, or a full system replacement. This chart shows the simple payback for a forced air system improvements with current incentives from Mid-America's rebate program included. And as you can see from the chart, all of them pay for themselves within 10 years. But what I found was really interesting was that combustion tune-up, it was free. Mid-America's program is allowing certified contractors to go into homes to check the efficiency of a system, and if they can gain at least a 10-point save increase, then they are offering the total cost for the combustion tune-up, which is roughly about $180. I thought that was very interesting. And now Bill's going to talk a little bit about the benefits to the different stakeholder groups.
The benefits of system verification impact all of these stakeholders. When programs promise or suggest savings, accuracy and transparency with clients and utilities is crucial. SAVE delivers these objectives by allowing us to develop an accurate scope of work and not relying on contractors' ideas. By training HVAC contractors, we establish a process with them that delivers uniform bids, eliminates confusion, and provides the best opportunity for our success as. There are several potential benefits for utilities. First, energy savings. Approximately 31 states now have energy efficiency regulations in place. Those regulations are built on savings goals and investment budgets. As I mentioned earlier, those savings goals are becoming increasingly difficult, particularly in residential and small commercial environment, where energy intensity profiles are lower and where fewer energy consumer devices. By elevating real efficiency, HVAC performance will help meet those savings goals. Second, evaluation, measurement, and verification, or EM&V. Verified savings is gaining steam in the energy efficiency business. I've even heard that sometime in the near future, verified savings will be required by statute. Because HVAC performance is measured and not deemed, it inherently introduces EM&V into a program where it's otherwise not currently offered. Third, many utilities are motivated simply to ensure their ratepayers are getting the full benefit of the efficiency investment they're paying into. HVAC performance creates a clear line of accountability for the contractor that protects the customer ratepayer. And last, peak demand reduction. Lowering peak demand is a critical issue for many utilities. Traditional heating and cooling practices are to underperform and oversize. HVAC performance mitigates those instances by ensuring optimal performance and thus preventing the need to oversize. HVAC performance also embraces the envelope impact, code calculations, and prior equipment selections in more difficult replacement environments. There are very good reasons for contractors to buy in. A contractor can instill trust in their clients just by scientifically measuring and analyzing the system. This level of trust is then enhanced by the fact that the promises made came to fruition. If a consumer has trust in a contractor, they will very likely recommend their services to friends, neighbors, and relatives. And word-of-mouth referrals are the strongest advertising a contractor can have. Most contractors will agree that callbacks are profit killers. When a job is done right the first time, increased customer satisfaction results because the client sees real savings. It also results in fewer callbacks and therefore increased profits. Many times people are disappointed in their purchase of high-efficiency equipment because the utility bill didn't reflect the deemed savings. A SAVE certified system will deliver the expected savings by delivering the BTUs to the rooms that is intended to condition. This results in increased comfort, which is a payback itself in many cases. SAVE can also eliminate the sound of restricted airflow caused by high static pressure. By having the static pressure at the manufacturer's specifications, reduce wear and tear on the blower motor. This is really a win-win situation. And now Tim will discuss how we at Elevate Energy have implemented the SAVE program.
At the assessment, oh yeah, by the way, that's my hand right there in that first photo all the way to the left. At the assessment, baseline measurements are taken to evaluate the system. The results from these tests are used to help us determine which, if any, repairs or adjustments need to be made. This data is also used to estimate energy savings and calculate the return on investment for our customers. When we place the data that we collected from the field into the SAVE web-based software, we're able to obtain a SAVE score I spoke about briefly earlier. The software not only gives us the score, but it also prescribes a list of possible solutions to address the issues with the system, telling us which repairs may need to be made in order to get the system operating at peak performance. After the repair work is complete, we then verify the work was done to the customer's satisfaction and test out the system to ensure that we have the results that we were expecting. If this was a complete system replacement, we would be retesting the system to verify the contractor's test results. By requiring commissioning, measurement, and verification for compliance of all new furnace systems installed, we are able to have a higher degree of transparency and accountability with our contractors throughout the system upgrade process. We pride ourselves on our high level of customer satisfaction and the fact that we are a single point of contact for any issues that might occur during the installation process. This is why our construction management team conducts 100% QA/QC of each job that is awarded to the contractors. All contractors know mistakes will cost you, and callbacks are even more expensive. If our team is able to identify a problem early into the installation process, we help our contractors by providing them the guidance and support. This translates to fewer callbacks, and for the contractors, this means better profits. This also gives our clients the reassurance that the job will be done right. Besides the measurements taken at pre- and post-installation, we also monitor utility data to accurately report real savings generated by implementation of these measures. We are using HVAC performance to identify efficiency opportunities as part of our pre-assessment process. We are also using it when existing equipment is underperforming by verifying current system operations. Also, when we are notified of premature equipment failure, we'll also investigate further if some of these issues may be present. Because a four-star system should have a life expectancy of about 20 years. So if a blower motor fails within 6 years, it will be prudent to check the static, since high static will make a motor work harder and longer. And finally, when a furnace is scheduled for replacement, having a pool of trained contractors allows us to set expectations high, get competitive apples-to-apple bids, without having to sort through unqualified proposals that are just simple cabinet stuffs. And now Dale's going to take us home, talking about growth and the trend of the SAVE program.
In the last 4 years, over 2,000 contractors have been certified, resulting in more than 30,000 quality installations. I think most businesses would be envious of the growth SAVE has accomplished. That's not by accident. Time after time, HVAC SAVE has made dramatic improvements on simple furnace swaps and new installations. Mid-American Energy, as well as others, offer really good incentives for HVAC efficiency, but to collect the rebate, the component or system must be SAVE certified. At Mid-American, an end user can get $900 for a high-efficiency furnace, but not without being SAVE certified. High-efficiency air conditioners have rebates from $675 to over $1,000, but again, it must be certified. Ductwork modifications also have robust incentives. All of these Iowa utilities offer incentives for SAVE certified installations, and there are others around the Midwest that are seriously considering adopting them. So what can we do? Start by initiating a conversation between utilities, implementers, and contractors in your area. Form a consensus. Conduct and attend these trainings. You can also reach out to program designers for advice. Mia is a fantastic partner to work with, so don't hesitate to contact them or us for more information. Here are some additional resources that you can look up if you're interested in pursuing this any further.
Thank you guys for your time. And we look forward to hearing any questions you may have.
Wonderful. Thank you very much, Tim and Dale, for your presentation. Just going to follow up with a few questions as we transfer back to transfer the sound back over to CEE. So as you pointed out, Dale and Tim, the SAVE program is just getting off the ground for Elevate Energy. Has pilot work given you an indication of the level of uptake that you anticipate to see from the marketplace in your area? Can you hear them? I don't know if we are hearing you. Let's actually, I think we weren't able to hear you if you were responding. Could you maybe just start from the beginning?
Although we have just started this work, it's been going on for years in Iowa and other states. End users of the market seem to like the fact that when these tests are conducted, they can rest assured that their system will be running very close to the efficiency it was designed to run at. Through testing and measuring of these forced air systems, greater savings can be gained than just a simple cabinet swap. It's not just the consumers that will benefit, though. In a survey conducted by SAVE, 62% of contractors polled stated that process of evaluation, optimization, and verification will, more often than not, result in more energy-efficient solutions. Contractors know these types of tests can give their clients and customers more value and a higher quality installation. In that same survey, contractors were asked if their customers valued long-term energy savings, in which the vast majority said yes. We anticipate that once this program is adopted by utilities and rebates are based on performance of installed equipment, that consumers will wonder why these weren't required before.
Thank you. I mean, the kind of the surveys that have been done, I think, are good indicators of, or hopefully great indicators of what you'll be seeing from the marketplace. So far, which stakeholders are showing the greatest interest in this work? I'm going to pose this to all the presenters, but Dale and Tim, are you seeing that contractors and utilities are the ones most interested in this program as of now? What about building owners?
We see interest from all of the stakeholders, really, because every one of them has something to gain from participating in the program. Contractors will have higher quality installations, better referrals. Utilities can reach their saving mandates. Implementers like us can develop the transparency needed to make our programs acceptable to our funders. And the consumers have a lot to gain for real energy savings.
Corey, I know we haven't drilled down into your content yet, but do you have any thoughts on this, on who you've seen kind of show the most interest around the ventilation system work that you've been doing?
Yeah, hi. I think contractors and building owners so far are most engaged. They know and have been working with these systems. They know the issues, the performance issues with these systems, and they're looking for better solutions. The outcomes of this research, and you'll see in my presentation, they're really practical. It's essentially lower cost ways to save energy, so it just makes sense, I think, from a bottom line running a building perspective to incorporate this stuff.
So with that, Dale and Tim, thank you for getting us started with the first half of the presentation and webinar, and I'm now going to hand it off to Corey to talk a little bit more about ventilation systems and energy savings on that side of the building.
Thank you. I'm excited to talk about this research project, Reducing the Cost of Effective Ventilation in Multifamily Buildings. Research findings ready for field implementation. So this is where I get to thank the Department of Commerce, Division of Energy Resources. This research was originally funded by a Conservation Applied Research and Development grant. So thank you to the Department of Commerce for making this presentation and this research possible. Are we good? Okay. So here is the agenda. I'm going to give a little overview of central ventilation systems, the ones we focused on in this project. Talk a little bit about solving the issues with these systems, go into a couple case studies, and then talk a little bit about how we've been taking the findings of this research into our field work here at CEE. So central ventilation systems, there are really two types of ways that you can ventilate a multifamily building, and one is with a centralized ventilation type system, and the other is with individual ventilation systems. Individual is what we're used to seeing in single-family homes where there's a bathroom or a kitchen fan that the occupant can turn a switch on to operate, and it's individually ducted to the exterior. That's not what we focused on in this research. We focused on centralized fans. Two examples are pictured there in the center picture and in the right picture, where the fan is serving all or large chunks of the building. So here's a closer look at typical configurations for these two systems. On the left is an exhaust system. You see there's a fan on the rooftop there that's serving multiple apartment units. So there can be a register and inlet in the kitchen or the bathroom, or both, as in this case. But they're commonly ducted to one fan. So that's the critical detail, is that there's multiple inlets on a singular fan. On the supply side, outdoor air is typically brought in and conditioned. This one happens to be on the rooftop. So the air is conditioned and delivered to typically the hallways in the apartment building. Hallways and common areas are what's typically served with a supply system. There may or may not be return air, as in this diagram, so sometimes it's just 100% supply air delivered via supply ducts only. This one has return air, where the recirculated air mixes with the outdoor air here in the air handler. Two ways to do it. The impact of these systems. So buildings with central ventilation systems, 10 to 20% of the total building energy use is attributed to these central ventilation systems. They typically run continuously 24 hours a day, and they have a big role to play in that they manage indoor moisture, odors, and pollutants for the indoor air. So what are the issues with these systems? The primary energy issue is that there can be excessive ventilation flow rates. Basically, they're ventilating more air than they need to be ventilating. There's an electric cost from the motors running these systems. There's the cost of ventilating excessive heated or cooled air, and then the comfort issue with excessive ventilation, which can be draftiness and motor noise, or duct noise. Lack of effective airflow distribution is another problem, or another issue, where there can be areas of high ventilation and low ventilation or no ventilation. Reasons for this: inlets can clog up over time. Balancing dampers, the devices that are meant to deliver even flow throughout the building, might be altered. Residents or occupants may alter them. And then the result is that there can be odors or moisture problems in areas where there's low or no flow. Lastly, these airflows are difficult to measure. They're large volume airflows, hard to access. They might be on the rooftop or other difficult places to access, and so they're commonly overlooked in building audits and other building consultations. Here's a look at where you might encounter central ventilation systems. So this is based on 250 or so building audits we did in the late 90s and early 2000s in Wisconsin. But you can see here that most of the ventilation system, centralized ventilation systems we found, were in 1960s and newer buildings. And then you can also see the green and red bar are 20 to 49 and 50 plus units. So larger buildings. So 1960s and newer and larger buildings are where we're encountering central ventilation systems the most frequently. So this research project, we looked at 18 buildings with central ventilation systems. We completed 6 retrofits on buildings that had an energy saving opportunity that was cost effective. And then another outcome of the research was this assessment and retrofit guide. So this is meant as a start-to-finish comprehensive guide for anybody that's looking to start incorporating ventilation assessment and retrofits into their work. It's meant to guide them through that process so that they can be equipped to do it. So there's a web location on this slide there in bold, and you can download that now. That's available. The final report is going to be published later this fall. This research also looked at trash chutes. Trash chutes can affect ventilation performance. They can, the purpose of a trash chute is to allow access for residents to drop trash into the dumpster from any floor in the building. Building air connected with this trash chute can cause odor problems coming from the trash chute. It also can draw excessive heated air up this chute, You can see that there's a passive termination here at the rooftop, and if this trash chute's connected extensively to the building air, there can be a lot of airflow via stack effect out the trash chute, so it can draw heated air out. It can be an energy cost. So odors and energy cost. I'll go into that a little more later. Here's what we found in the research. Of the 18 systems that we looked at, 7 of the 11 trash chutes had a cost-effective energy saving opportunity. 3 of the 16 supply systems had a cost-effective energy saving opportunity, and 6 of 12, or half of the exhaust systems, had an energy saving opportunity. So a decent frequency where we're finding buildings with central ventilation systems that also have an energy saving opportunity. So I'm going to go into a little bit about how we're solving these ventilation issues. What it boils down to is reducing excessive ventilation flow to get the energy savings, but then also balancing the flow so that it's adequately distributed throughout the building, so it's effectively dealing with moisture and odors and pollutants. Starting with trash chutes. As I mentioned, so here's my diagram again of the trash chute down in the corner. And as I mentioned, if this trash chute, typically this is enclosed in a fire-rated wall wherever it's inside the building. In reality, or that's the way it's supposed to be designed. In reality, there can be a lot of connections between the chute and the building air. So that can cause odor in the building. It can also, during cold months, cause excessive airflow via stack effect up and out of the building, drawing heated air out of the building. So the ways to resolve that sometimes are really basic, like keeping the trash room door closed. Particularly down in this dumpster room, this trash room door can be propped open, for moving dumpsters around and stuff. Recommending to close that will solve a lot of the issues, energy issues and odor issues. Sealing the trash room off from the rest of the building. So if this is in an enclosed, if the chute's in an enclosed area throughout the building as it should be, there may be air sealing details that you can handle in that enclosure. Maybe there's a penetration around pipe or ductwork that can be sealed to help isolate the chute air from the building air. If there's no door or no room that's isolating the chute from the building air, this is common on the dumpster room floor, so on the bottom floor. We'll see where there's not really a separate room for the dumpster to be in. Maybe there's storage areas down there, office areas, lobby, that's allowing chute air to access building air. If that's the case, we did a retrofit in one building where that was the case, and we enclosed the bottom of the chute. You can see the picture on the left was the before. The picture on the right here at the bottom is the after. We enclosed the bottom of the chute to the top of the dumpster to isolate the building air from the chute air. And then reducing the chute cap opening. So you can see on the upper right-hand corner is the cap, the rooftop termination. And you can see this cap has, looks like about 12 inches of open area here. You can see there's actually trash being sucked up into the bird screen here because there's so much stack flow during cold months. So reducing this area, moving this, reinstalling this cap so that it's lower so that there's just 1 or 2 inches of open area was the solution here. Energy savings from these little modifications are difficult to quantify. We did quantify it on one. This is actually one retrofit we did on a singular chute. So the cap, we did this modification where we lowered the cap and then did this dumpster room modification all in the same building, and they saw about $1,500 per year in annual energy savings. But we had to do some long-term data logging in order to get an estimation of what their savings were. It's very weather dependent. So hard to quantify. Basically, we're kind of recommending these as prescriptive things. Check these boxes, making sure that these 4 items are handled in the building helps you successfully address trash chute issues, but also will help you have a more successful building ventilation outcome if you're addressing supply and exhaust systems in tandem. Supply systems or makeup air systems. The solution here, if you're measuring and determining that they're bringing in excessive outdoor air, the solution is simple. It's reducing the fan speed. This can be done with a control adjustment in the simplest case, or a resheave of the fan, which is a way of saying they're changing out the pulleys for reduced fan RPM. And then, of course, there's a pre and post airflow test to verify or to document the energy savings. This is standard work for a test and balance contractor, and usually ends up being done in a day. It's low cost, high return, kind of a no-brainer decision for a building owner to make in the event that they do have excessive outdoor air being delivered in their supply system. So the barrier is finding these systems that are delivering excessive outdoor air. Here's a retrofit we did on a supply system in Minneapolis. We found it was delivering 70% more ventilation air than was recommended for the building, even with a dirty intake screen and heat exchange coil. So still excessive, even though their intake screen and heat exchange coil were interfering with the flow. So we recommended that they clean the screen and the heat exchange coil, and then resheave these. Here's the sheaves or the pulleys here, changing those out for reduced fan RPM. Here's a look at the energy savings. They saw just under $7,000 per year in annual energy savings. Payback was 2 months, so really short-term payback. Now I'm going to move to exhaust systems. There's really, when you're retrofitting exhaust systems, there's really 2 parts to it. You're changing out the fan here at the rooftop in most cases for reduced exhaust flow. And then you're dealing with the inlets here. There's balancing devices typically at each inlet, and there's a recommendation that we have for that to maintain balanced flow from top to bottom of the duct or the shaft. So here's the rooftop detail where we're changing the old fans that are typically belt driven. You can see there's an example of a belt driven fan here. We're changing these with EC or high efficiency motors that have speed controls on them that you can turn down. So this allows you to be able to turn down the speed of the motor. The other detail at the rooftop is this detail here on the left where we're sealing the curb below the fan. So this is the duct coming up in the bottom of the fan is tipped up here. And you can see that there's foam here that's sealing the gap so that all of the air that the fan is drawing into it or exhausting is coming from the duct and not from unintended places like the roof cavity. So that's the rooftop detail. At the inlet, so in the apartment units, you take off the register and you might find one of these devices. So this is a constant air regulator or a car, and this is a balancing louver or balancing damper. The car, the constant air regulator, is a self-balancing orifice. What it's designed to do is monitor the pressure in the shaft or in the duct and adjust the opening size according to the pressure. One issue with these is that after a couple years of operation, or as low as a couple years of operation, the pressure monitoring portion of this device gets crudted up. You can see that this one's pretty dirty after a few years of operation. So this one got pretty dirty, and it no longer self-adjusts. So that's a problem. Once they can't self-adjust anymore, they're just an orifice, so they don't have the ability to balance anymore. Balancing louvers here, these also have the potential to clog up, but another issue with them is that occupants may adjust them or alter them. They're right behind the register, and they may open them or fully shut them, and that affects flow not only to their unit but to the whole shaft or the duct that multiple apartment units are on. So the solution is this picture on the right here. It's basically a piece of sheet metal with a hole in it, and the hole is sized for correct flow at a specific shaft pressure. So this is a really simple solution that doesn't clog up over time, and it's much cheaper. It's $5 to $7 versus $30 to $40 for one of these guys on the left. So this is a great solution that's low cost. This is the other detail we're handling at the inlet, which is just air sealing the duct here where it meets the ceiling. So this is right after you took off the register cover. You'd see maybe some gaps between the ceiling drywall and the duct, just to make sure that all the air that's drawn up into the duct is from the apartment unit and not from unintended places like ceiling and wall cavities. Again, you can see that this has been sealed with mastic. So here's a retrofit that we did in Minneapolis again. We measured their exhaust ventilation flows at 48% higher than the recommended rate for the building. And they were having odor and moisture issues, particularly in their bathrooms. What the retrofit entailed was replacing the operable balancing louvers, like we saw in the picture before, with fixed orifices, the sheet metal with the hole in it. Replacing the rooftop belt drive exhaust fans with high efficiency types with speed controls. And then we did a pre and post airflow measurement. Here's a look at what happened before and after the retrofit on a kitchen shaft. So this building had, I think, 10 or 12 shafts. Some were serving kitchen inlets and some were serving bathroom inlets. This one is top to bottom inlet flow measurements on each floor of the kitchen airflow. And you can see that there's high airflows, which are dark reds, and then the pinks are the low airflows, kind of below the recommended amount. And then when we're right within the tolerable recommended amount, it's white. So you can see the pre-retrofit, a lot of dark reds, there's a lot of high airflows, a lot of energy saving potential. After we installed the fixed orifices and turned down the fans, you can see we're on this shaft 100% within good levels or tolerable airflow levels. So great improvement, lots of energy savings here. Their bath shafts were, they tended to be a little bit more like this. Airflow was all over the map. This is on the bath shafts, they were serving 2 back-to-back bathrooms on every floor. That's why there's 2 measurements. And you can see there's some dark red, some high, some pink, which is low to no flow, and then some good flows, kind of all over the map. And this is where they were having the odor and moisture issues, particularly. This is kind of where the problem was. Post-retrofit, we resolved most of that distribution discrepancy, so now we're pretty even top to bottom with a couple of exceptions, a couple of oddball inlets that we couldn't resolve on this shaft, but generally speaking, a great improvement in the way that their ventilation system is performing. Overall, when you put together the energy savings from the kitchens and the distribution improvement on the baths, we still came out with a decent amount of energy savings, about $5,500 per year in energy savings, which yielded about a 6.2-year payback. A little bit longer term payback than we typically see with our energy saving retrofits, but I think because of the fact that we're solving odor and moisture issues for these building owners, they're motivated to invest to improve the performance of that system. So I'm going to transition here to talk a little bit about how what parts of this research we are using in our field work currently. One of the cool outcomes of this research is that we found a more efficient way to measure airflow, measure exhaust airflow in particular. So this picture on the left here is showing what we originally started off with and what a lot of energy people start off with, which is powered fans on the rooftop to measure these mushroom-style PRV fans. This is the exhaust fan. It's difficult to measure these. There isn't really a device that is out there to do it, so we started on sort of figuring out if we could make a device. These are duct blaster fans mounted to the top of a box, and you can see there's extension cords, hoses, and 3 people lifting this heavy box. By the end of it, Jim Fitzgerald kind of landed on this prototype, which is using the Energy Conservatory's True Flow meter. This is a meter that just uses the DG700 gauge. There's no power required. Lighter weight, one person can operate and move this box around. So you get a flow measurement that's more accurate with lower cost equipment in minutes rather than in hours. This was a really great improvement on efficiency for measuring airflows. The Multifamily Ventilation Assessment and Retrofit Guide, I think, is going to be a great resource. It walks you through identifying the systems, to measuring airflows on the systems, to making recommendations and developing work scopes, to verifying a retrofit after a contractor has done a ventilation retrofit. There's lookup tables and decision trees. It's meant to be a very pick up and go resource that sort of minimizes the number crunching that a building consultant would have to do to be able to do this work quickly and efficiently. The way that this process is working into our multifamily programs here is that we're screening the building for the opportunity at our audit, which in Minnesota here, ours is free to building owners, so they get a free energy audit. That's where we're doing this ventilation screening, and we're trying to determine, is there an energy saving opportunity or isn't there? If there is, we're recommending that they go into more detail, getting some more diagnostic work and a work scope written up, and we're providing that service as well. We're taking more in-depth flow measurements and determining how to save energy and then solve their distribution issues. And we're also verifying the retrofit post. We're verifying the airflow post retrofit. So after the contractor commissions the airflow, we're coming and checking on the commissioning just to make sure it is within design parameters. And I'm going to echo Elevate's keys to success. We're providing that single point of contact. It does improve customer service. It's making the process much smoother. We're looking at or verifying 100% of jobs, similarly to Elevate. And I think with ventilation, we're addressing the distribution problems in tandem with the energy savings. So we're getting those non-energy benefits and stressing those equally and doing as much QA on those as we are on the energy savings. And I think that's an important value add. If you would like, you or anybody you know would like to learn how to use the ventilation assessment and retrofit guide, measure airflows, etc., we're conducting a training. It's going to be free, and it will cover the topics here, listed here, basically all the topics that the assessment and retrofit guide covers, and I am the point of contact for that. So you can contact me if that's something you're interested in. And that's all I have. So thank you very much.
Wonderful. Thank you, Corey. That was really a wealth of information. I think that the guide will hopefully be a wonderful resource in the trainings as well. So I encourage anyone on the webinar today to enter any questions that they have, and would love to get to them. But I do have a few follow-up questions, some things that I really wanted to ask as follow-up questions as a listener myself. And so I find it interesting that both of the areas of focus we touched on today point to deeper work around static pressure and pressure flows. Do you think this is an indication that building science is penetrating our energy savings program design and research methods more successfully or more deeply? Maybe getting beyond some of the lowest hanging fruit. I'm curious on any of your thoughts. Dale and Tim, do you have any initial thoughts on that?
You know, I was just thinking that system efficiency at commission should be standard practice. We feel by highlighting the issues around this type of fact-based performance testing is key. Instead of just picking contractors with the lowest price, if system efficiency is conducted when the system is installed and necessary corrections are made then, any extra costs to the consumers are minimized. The days of low-hanging fruit are just about over. We need to dig a little deeper to get more savings from our systems.
Thanks, Tim. I don't know if Dale has anything else, but Corey, any thoughts from you?
Yeah, I think that ventilation isn't a universally applicable energy efficiency measure, and I think in that way it's probably not low-hanging fruit. You have to measure, or you have to conduct some assessments to be able to find the opportunities. So there is a need for measurements and for diagnostics to sort of penetrate our walk-through audits. So I think that is I think that's an indication that we are having to dig a little bit deeper. But when the energy savings are there, they're great. So that's an important point.
Right, worth the deeper dig.
Exactly.
Right. So something that I think is really important and vital because it's different between the two presentations and the work that each organization is doing is sort of the characterization of both the individual furnace system improvements and the central ventilation upgrades. So the different building stocks that we're focusing on here and or the timing that this work can be done. So Dale and Tim, can you give me a little more detail about the primary building characteristics or the kind of the timing points of entry for doing this work?
Okay, you want to take this one?
Sure. There isn't really one particular building type. We work in a multitude of building types, large multifamily, small multifamily, single family, and mixed use. But what we do look for are forced air systems. However, there is significant advantage to implementing these strategies at specific times. For example, besides new construction, you couldn't find a better time than during a gut rehab. This gives the contractor most flexibility when designing the duct system, which is a major part of system efficiency. However, most of the buildings we work in are older multifamily or mixed use and not-for-profit buildings.
All right, so it does tend to be more of a timing component, but working on a variety of building types, but where there's a lot of major renovations, new construction. Corey, how about for you?
Yeah, I think for us, we're going into, in our auditing programs, going into any type of building. What we're noting for that would be more likely, as I noted in my presentation, buildings that are 20 units and larger and newer than 1960 are basic parameters that might indicate that they might have a central ventilation system. They tend to be buildings that look like this. High-rise buildings most frequently have these type of systems. So again, we did a little bit of digging to kind of exemplify the opportunity here and abroad in other states. Here's a look at United States building stock by age category. You can see there's a strong proportion of multifamily units excuse me, that are built 1960 and newer. So that was that age category where we were seeing a lot of ventilation systems. We looked at Minneapolis. This is looking at buildings that are 20 units and larger. And you can see the dark green covers a significant area in the Minneapolis area. Dark green is 5.2 to 8.8% of total of buildings are 20-unit multifamily buildings or larger. So a lot of opportunity here in Minneapolis. As an example, we looked at Seattle. Seattle on the left, multifamily units built before 1960, and on the right, units built since 1960. You can see a lot of, many thousands of units in Seattle as well. And then looking at greater Minnesota, this is from the Energy Center of Wisconsin and Franklin Energy study a couple years ago. Sample of the buildings they looked at, and you can see 27% were 20 to 49 unit buildings, and 21% were 50 or more unit buildings. So total of 48% there in the 20 and more unit category. So strong opportunities here in Minnesota and kind of across the nation. Oops.
Well, that's great. Yeah, those are really helpful reference points, knowing that there are opportunities not just in urban areas and not just in cold climates, coastal climates as well, and other climates. So each of you touched on actions that our listeners could address, but this is a pivotal information point, kind of the recommendations that for listeners or even asks that you have for them. Could you maybe summarize in just a few sentences what those are for the stakeholders that we know are listening today based on the polls we had earlier? Corey, maybe you could take this first.
Sure. I think for utilities, it's providing a rebate or a program path, or making sure that your implementer is including this in their programs. For building owners, I think if you have these type of systems, you're probably already aware of the issues with them, but we can help connect you with next steps and help you get assessments and diagnostics done on that equipment. Designers and developers, I think we can adopt this technique of balancing with the fixed orifices into building standards. I think there's a great opportunity there. And then also verifying airflow. There's some opportunity there as well. And then contractors and energy efficiency implementers, I think that the training that we're conducting this winter, and then the manual, the assessment and retrofit manual will be great first steps in getting, the key is getting more people doing these ventilation assessments, and I think those will really help with that.
Dale and Tim, any kind of high takeaways, things you want to kind of bring home as we're nearing the end of the presentation and kind of getting into some of the Q&A from the audience?
Yes, definitely. I guess we'd like to start by just saying, look into the SAVE program. The SAVE program is excellent. It not only looks at combustion efficiency, but it also looks at the charge for the AC units, and it also looks at static pressure and delivered BTUs. So many benefits to the SAVE program. Also, one thing that we didn't mention earlier is that there's an online database. So when you input all the information into the system, it's saved and it's stored online. So if you ever need to look up any information about a particular project, it's only a few clicks away. And also maybe national standards around furnace commissioning. That's a big thing. We would really like implementers and utilities to be behind a national push for that, with standards set around furnace commissioning.
Great, thank you so much.
Yeah.
Oh, Dale, go ahead.
I'm with Jim on that topic. It would be really important or really impactful if utilities decided to require performance-based incentives that aren't just based on AFUE.
Yeah, way to reinforce that point. Thank you for that summary. And a question from an audience member is, and I believe this is referring, this question is for Corey. Does your program of reducing ventilation rates take into account design decisions to pressurize corridors so that odors are not shared between apartment units?
Yeah, that's a good question and a great concern. I think, in every building that we're talking about retrofitting the ventilation system, it's a discussion with the owners. In altering that design, a lot of the design, what we're finding when the original design was to pressurize the corridors, that it's not effective. The corridors aren't actually pressurized. Maybe a small portion is, but generally speaking, it's not minimizing the odors the way it should. So the way that we've been, or I guess the most typical way that we're dealing with this is we're recommending a balanced flow. So we're giving the corridors the same cubic feet per minute of airflow as is being drawn from the building by the exhaust system. And this is not dealt with on the code side. Code officials don't particularly get into the weeds like this. So it's usually just a discussion with the building owner and how they want to deal with it, how they think their occupancy would respond to reducing the ventilation rate, and generally that's worked in the buildings that we've altered or retrofitted.
Another question from the audience member is, can you discuss the impact of duct leakage and solutions? It's a little bit open-ended. I think that's more intended for Corey. Do you have any thoughts on that?
Yeah, the impact of duct leakage. There is duct leakage can be sort of a wrench in the system, and we've had some success with AeroSeal. There's a product that you can, an aerosolized product that can be injected into the ducts and seal to some success. I think the thing that we're looking for is, are the ducts in relative tact? And if they are in relative tact, this AeroSeal product can be a great solution if there is a lot of duct leakage. The issue around duct leakage is if there is a lot of duct leakage, no matter what you're doing to the ventilation system, it's not going to work very well. You're going to have low to no flows on the far reaches of the duct and high flows near to the fan. because of the duct leakage. So sometimes if there's a lot of duct leakage, you'll have to deal with that as part of the retrofit. So the AeroSeal product can be a great solution. We also had some success when we were running into the issue on certain shafts of duct leakage. Just going behind sealing access panels and doing some spot duct sealing where we could see maybe connecting disconnects and sealing up spots where we could see that there are big air leaks or missing access panels, stuff like that that you can resolve easily.
I believe just one more question from the audience before I ask what might be the final question for our presentation. We can wrap up just a few minutes early. And again, I think this will be kind of quick, but Corey, after you reduce the ventilation rate, do you take pressure readings to ensure that the building remains positive with respect to the adjoining parking garages as required by code?
Yes. Yep, that's advisable. Yeah, we didn't, in the retrofits that we've done so far, we haven't encountered a parking garage being associated with it, but yes, that's something we're checking out.
Excellent. So for me, the final question I have is, what is it really going to take to deploy the strategies that all three of you talked about, to take them to a large scale? And perhaps those are two different pictures. What are the conversations you are inviting to help increase scalability and impact? Elevate, Tim or Dale, do you have any thoughts on that?
Well, we do need more utilities to require performance-based incentives, as I mentioned before. There needs to be more information provided to consumers to educate them that there is a better way and there may be a problem with their system and the possible lack of real savings. Increased awareness and higher standards will provide the market with the tools that consumers need to make more informed choices when it comes to true system efficiency. And changing the incentive structure to deploy efficiency instead of AFUE will help these strategies become more like common knowledge.
Thank you. Corey, any thoughts?
Yeah, I think that the primary barrier with ventilation retrofitting is that the assessment needs to get done, and I think that can be a barrier if it costs money, or if it's not clear, what the payback is going to be on energy savings. So I think getting assessments done is key. Solving the issues for doing a low cost assessment was one big focus of this research, knowing that building owners wouldn't want to invest a lot on a mystery project of they wouldn't be sure if they would get energy savings out of it or not. So the training and the assessment and retrofit guides sort of outline a low-cost way to assess buildings and then low-cost way to retrofit them, and I think that might address the barrier of people not looking into this in buildings very frequently yet.
Yet. That is the key word, right? Well, I would like to say thank you to our presenters today. This has been, I think, a really great collection of information in multifamily work being done that's really kind of quite innovative and in the Midwest, but usable across the country. As you can see on your screen right now, there's a webinar archive link, which is where you can find this webinar recording, as well as all of CEE's webinars are archived at this location in our resource center. How you'd navigate there from our homepage, and this is where you'd find it, that upper right-hand corner under webinars. As I mentioned earlier, if you're interested in learning more about other research and resources that we provide and create, we would love to have you as a newsletter recipient, which you can sign up for in the upper right-hand corner. And finally, if you are interested, follow us on Twitter at MNCEE, where CE helps share news and ideas on energy policy, technology, and research locally and at the national level. So with that, I thank you all very much and have a great afternoon.